Hi, welcome back. And for the 11.14, and that is we have to prove that there is some constant rho, and so that the rho gap and Q constraint satisfying problem is NP hard. So, and what we are going to do is that we can observe that if for any 3CNF instance, and if it is not satisfiable, suppose we have a phi that has a n constraints, and if it is not satisfiable and there is at least one constraint that is not satisfiable, so so actually we can immediately have that the value of phi, if it is not satisfiable, then the value of it is equal or less than 1 minus 1 over m. So, but this error here is not a constant because it just depends on the number of constraints. So what we are going to do is to amplify this error here. So suppose we have some error, and that means if phi is not satisfiable, then there is at least epsilon portion of the constraints that will be violated. So, and the Dinah's proof here, she actually amplified the here, and that is we can reduce the phi here and to another, say psi, and the value of psi is, if it is also if it is not satisfiable, and we can have much less. The gap is amplified here, and so the epsilon prime is some greater portion of to the epsilon. And suppose we can find some reduction here, so that the gap here is amplified into about by a constant factor of 2. So we can repeat the same reduction many times. So say we can repeat it to log. Suppose we can repeat it by log m times. Then the number of the factor here is also can reach the m. So we can finally get the some constant we predefined here. So that's the main idea, that we want to amplify this gap. Okay, and so by reduction we means that we can have some definition of complete linear blow-up reduction. That is, if we are going to reduce some QCSP instance into another constraint satisfying problem instance, we need to preserve some factors so that we can go through the reduction very smoothly. And so for a constraint satisfying problem instance, the most important thing is the arity, which is the number of related variables in each constraint, and the alphabet size, and which means we can enlarge the alphabet size to not only binary value. Each variable can take more number of value, but this number is a constant here. So and the number of variables and number of constraints and the number of value. Okay, so suppose we have from the previous thought we have some like if we have some Q0 arity and the actually in 3CNF it is 3, right? So the alphabet is 2, which is binary. Okay. And the number of variables is like n variables and number of constraints m, and the value is epsilon, and we know that it might be like something like 1 over m, but if we fix some epsilon here to be a really small epsilon, and for our gap amplification lemma, and we can do some change into the complete linear blow up reduction here, and then we can do some gap amplification lemma here, and so and finally we can get we can reduce the number of arity into 2, but as a trade-off, we increase our alphabet size to W, which means 1, 2, 3 to W number of alphabets, and the variable numbers will be increased, but increased by not much. By not much, we mean that it is linear to our input size, so it's like something like something like this, and number of constraints will also be increased like this, and the value here will be the gap here will be increased, so it's like this way, and in the final we want to increase the gap by about 6. Okay, so after we have done this gap amplification things, we can do another called a alphabet reduction here. So that the number of arity and becomes Q0 again, and the alphabet number becomes 0 and 1 again, and the number of variables is something is linear or unchanged things here, and some constraints. The number of constraints is another time a linear blow up, and the value will be shrink, but not shrink too much. It's just stop by a third, 1/3 here. So after we do a gap amplification and alphabet reduction here, we get with a linear blow up constraints and a not much variable, and we can amplify the gap here by a factor of 2. So after this iteration about to the say log m times, we can reduce the original error gap here to something is we have predefined epsilon 0. So actually we have done that. We can find some row here, and some Q is actually 3 in the 3CNF form if we take the set as a complete problem, and then we have done our hardness of approximation view of the PCP 0. So in our proof, we will only cover the first lemma here, which means we can do the amplification. There is some complete linear blow-up reduction so that we can have a really large gap and some constraints to be linear time more and variables is linear more, and we can have some trade-off here. And actually the alphabet is quite large, as we can see. So before we go into the actually gap amplification, say here we have to adjust some of the some instance so that we can after we tweak some after some reductions, we can have a better form so that we can powering, by powering, then we say powering means we can enlarge our gap of value. So actually we can have in the gap amplifications thing here, we will do some steps, and so that actually we first want to reduce them into a nice form, a nice instances. So this is the original one, and we want to do some be the nice form, and then we can build some really. So in the second step we will do the powering thing, but in the first we must reduction first to get a better form so that we can manipulate it in a better way. So in the first we have to lower the arity here, but with trade-off we will increase our alphabet, and the number of variables may change in a linear way, and the number of constraints will be some constants, and we lose some gap here. So say by some constant number, something like this. Okay, and then we will do another thing here later to close the gap here. So my part is to prove that we can change the original phi here to a nice form. So by nice form, we will introduce some concept here, and the concept is the reason that we want to reduce the arity into 2 is that we want to introduce a concept called constraint graph here. So so actually consider a 2 CSP problem here, and we can have the constraint graph, because for every constraint there is it's just related to 2 variables. So suppose we have 2 variables here, and we will have an h here. If they have some constraint, they have got some constraint here, and like vi, vj, vi, vj, something like this, and hope so we will manipulate something inside here, so to get a really nice form constraint graph, which is a good deregular expander graph, and so that we can do powering method after that. So to get a good form, we will say that we now define what is a nice instance here. And the nice instance will be, first of all, it is the arity is 2. So the priority is 2. The second one is the constraint. We consider the constraint graph. The constraint graph here is it is deregular. So, and D here is a absolute constant. So a deregular graph here, that means each variable xi is appeared in only D constraints here. Okay, and the third one is that this deregular graph is an expander. An expander graph. Okay, so by means of expander graph, we say that actually the lambda, the norm of the graph here, is less than some constant less than 1. So in the textbook, we say that if lambda is less than 0.9 and the graph is actually a good expander here. So this is first we want to show that for some input phi here, and we can reduce them through a complete linear blow-up reduction, so that after reduction the promised problem becomes have this good form, the instances. Okay, so so now we are going to do actually the reduction part here. So the first one the first thing we want to do is by the claim 22.36, we want to reduce the arity. So we want to do something like if the arity original is Q and we want to let them down to 2. So actually the arity is Q and the number the number of alphabet is binary already originally, and the number of variables and the number of constraints m, and the value is something like 1 minus epsilon. And after we tweak the instance CSP instance here, we will get a 2 arity, which is every constraint will related to 2 of the variables, and but we lose the number. Actually, we have 2 to the q number of alphabet. So it's actually the each state of each q variables in the constraint before, and we just encode it into a larger alphabet set. So the number of constraints will increase here, and the number of variables increase here, and number of constraints will also increase, and the gap will also be shrinking by 1 over q. And how can we achieve this? Actually, it is simple. We just encode suppose we have a constraint phi I here, and it is something variable to 1x1 to x q here. And actually, we create a yi variable to denote the assignment of all the x1 to xq here. So more formally, since the x1 to the xq is belongs to the original set of x's, so we cannot write this. We use the u1 to uq here to denote the actually is a subset of the original variables. So each yi, so we now have new variables here to denote each constraint. y1, y2 to yn, and together with original variables here, x1 to xn here. So we can have some new constraint, because each yi takes the value of each yi takes the value is from is a q tuple of 1 to 0 or 1. So so each yi encodes what will behave in the u1 to uq in the original constraint here. And if we have yi for each yi and each xj here, original variable here, and the constraint says that first of all the yi assignment to the u1 to uq here must be satisfied by phi of I, and also the xj corresponds to the u1 to the assignment is correct. So after this, we can see that it is a complete linear blow-up reduction, because by completeness, if there is assignment of x1 to xn such that each set phi of I is satisfying. So of course the new constraint here is also satisfied, because if we just set the yi to be the assignment of these x's, and it will be assigned, it will be accept here. So so actually it is complete. The completeness is true, and also the linear blow-up thing is true, because for each q is a constant here, and for each constraint and each variable, so we have a new constraint here, and the new constraint number of new constraint is exactly q times n, and the number of variables becomes n plus m here, because we just put every q tuple variable assignment here to be a new variable. So this is satisfied, this is satisfied, this is satisfied, and this is satisfied. For the last part, the value part is the gap will be shrinked. So suppose we have suppose the original phi is not satisfiable, so there is some satisfying assignment. There will broken up by some epsilon here, and okay, so there's the epsilon times m number of constraints is not satisfiable, and we pick them out, and we find that for each of the q constraints here in the new settings here, and at least one constraint will be broken, because it will be violated, because if it is all satisfied, then the original phi of I is also satisfied. So the number of not satisfying violated constraints will remain the same number, but because we increase the number of constraints, so the number of value is shrinking by a factor of q. Okay, we have done the first part, and we get a error t here. We reduce the error t from q to 2. So what we have to so this part is satisfied. So we want to do the second part and the third part. The second part states that we have to, after we do the error t reduction, we get something. The constraint graph will be something like bipartite or something. So actually, we want to make them to be deregular. Okay, so now we have some two arity is 2, the alphabet suppose is W, and the number of variables is n, number of constraints m, and the arrow is epsilon here. And we want to build, reduce them into another 2 CSP W instances so that the constraint graph is deregular. And also the value, it is completeness, and the value is the gap will not shrink too much. So by that means we reserve the number of constraint, number of arity, and the number of alphabet set, and number of variables, number of constraints, and the number of is by not too much. Okay, so this the number of variables will be increased by something like n times some linear fraction, linear vector of n. It's say actually it's some polynomial of n, and let me see. No. It's actually okay. So it's another linear blow up number of variables. Okay, so that our proof will complete. And this thing is, at first we look at the constraint graph here, and for each constraint, each n constraint, we have an edge connecting them, and now we want to do that is to apply some transformation so that the final graph is deregular, and actually it is have some good error bound here. And what we are going to do is, suppose there is a variable that appears in some k number of graph, and there is some k number of the graphs, and we just change them. We just create another k number of variables, so that it becomes something like this. Okay, and the inner part of the graph is something having good expansion and a d-1 regular graph. Okay, so we know that there is a graph, and from the chapter 21 we know that there is a given some d lambda or something, and we can have some good expansion graph with a d regular and vertices. So suppose we pick out like this Gn, and Gn will be some n d-1 lambda expanded graph. So actually we just, after we split the variables into k different variable here, we want to maintain that if it is have the same assignment, then these k assignments, these k variables must consist with their assignment. So if we connect this by a expander graph, then we will give every constraint that the two nodes here with an edge, they have the same number, they have the same assignment. So that if it is satisfiable, then this new splitted graph is also satisfiable. This is a complete part. And also the number of constraints becomes n plus dm, because each variable here will be split out into k, and the k is the number of original constraints here, and each node will increase. Then we will add another d minus 1, something, okay, d is not, okay. There will be add some d minus 1 constraint here, so that each node will become a d regular. Okay, so yeah, the different part from here to the textbook is the textbooks assume this is d, and they found that this d plus 1 regular actually. So yeah, so I think it's more consistent here. And so this is satisfied, this is satisfied, it's unchanged and unchanged. So the last part of it we have to do is to found the error here. And the bound error here, things we have to do is use some okay, the whole picture is like this, and suppose we have, this is phi, and we map it into psi here, and suppose phi is not satisfiable, then also the psi is not satisfiable. So okay. So if the psi is not satisfiable, and we want to construct some phi so that we can prove that by the condition here, and we can find at least some portion of them is also violated in psi here. So how can we do this thing? Okay, so first of all, we have to for suppose that we have an assignment for psi, which is y1, y2 to ym. It's and for each yi, we split into the number of k number of nodes here. So we have one y11 to y1k1, y21 and to y2k2 here, and yn1 to ynkn here, and the sum of it is most linear. And okay, we have a lot of variables, and how can we find some variable some assignment here when we get an inconsistent assignment, because it is not satisfiable, so we can just find some assignment here, and they may be different, so that this constraint is not satisfiable. And so after this, we get we can take the majority of them. Means that the most appearing value here becomes the choice of y1 here, and the most of the value here becomes the y2, yn. Okay, so after we get the majority, something like called with most number of values here, and we will get some assignment to the phi here, and since it is not satisfiable, so at least epsilon times m number of constraints in phi will be violated by this assignment. And now we want to show that actually the number of fraction number of the non-satisfiable violated constraint here is phi number of it's epsilon m over 100 of w. So after this, we divide it by the number of constraints, we get our gap result. Okay. So first of all, we consider to prove this, we consider the two cases here, and so for this assignment, we define Ti to be number of variables here in psi, which is not coincide with the final choice here. So we denote Ti to be number of Yij such that Yij is not equal to the final choice here. And since we take the most appearing value here, so by the pigeonhole principle, we get the number of Ti is at most Ki times 1 over W. That means the most appearing value is the same and all others are different. So okay, we split the cases here into consider two cases. First one is the sum of all disagreement here is greater than say 4 epsilon times m, something like this. And okay. For the first part and second part, the first part we are going to use there are a lot of disagreements, so we can actually give a thought that in the expander graph inside each variable there are a large portion that they will be violated, and when the Ti is really small, that because a lot of variables is not a lot of variable consistent with yi that's our choice, and our choice in the original phi here is not satisfiable, so they may violate the epsilon m here. So for each violated epsilon m here, they will give inconsistency to the large number of the wrong assignment. So the assignment here will be violated. This is correct assignment to our choice, but this choice is violated if it is correct. This is correct, and in phi this constraint is violated. So there are a lot of large portions they will be violated here. Okay, so the first part here, how do we prove it? It is violated by some number constant fraction of the constraints. Is to say that okay, and we know that the Ti is at least 0 and at most Ki times 1 minus 1 over W. And so since inside here is an expander graph, so we can estimate the number of violated constraint H here. So by expander, we say suppose this is the same agreement to yi. Here is the same with yi, and the number of disagreement. The number of disagreement here is ti, right? There's the ti number of them, and the total number of vertices is ki numbers. So between the two classes, since this is a good expander graph, we say that a good expander graph is pick something is less than have the norm less than 0.9. So from the exercise 22.1, actually we just plug something, and we can get the actually we have this as a good expansion. So a good expansion will give us a good result, the good number here, and this given by number of edges is at least okay, it's at least that much. So after we plug into this part, we have to consider the both sides, and we take the smaller part. So if ti is the greater portion, and we just pick ti, if ti is smaller than ki over 2, we can take ti as the set size here. And if ti is greater, we have to pick the ki minus ti. And from the constraint here, we get the ki minus ti is actually is greater than something like this. 1 over w times 1 minus 1 over w. Okay. So when we plug in these things here, and we find that there are at least such number of edges here, so we can get a number of edges between the truly the same assignment 1 to the disagreement 1. Here, the number of edges is by at the most ti times d over 2 times 1 minus lambda over 2. So this is at least 1, so we just drop it here, and we get 0.1, 0.9 over 4. Something like this. Sorry. 0.1 here. Okay. So, and the number of alphabet, we can assume that it is at least 2. So this part we will get 1 over 2 here. Okay, so for each I, we have found at least this number of portion, this number of edges is this arrangement which is violated in the side. So we just take sum of them, the summation of them, so that the ti sums into greater than epsilon m over 4. So this is greater than this is greater than say 4 to this 8, so it's 80. It's 80 W over epsilon m. Oops. Just overestimated. Oops. It's 320 W over. And we got some loose of factor here, so maybe we can just adjust them into a better estimate. So actually, it's the proof here we have some constant trade-off to the number of this. And okay, so after the second adjustment, we get a deregular graph, which is just lose some constant factor of the value here, and we increase the constraint and the variables by linear way. Okay, so and actually our construction can be done in polynomial time, which is acceptable. And the last part we want to do is to make the whole constraint graph to be expander graph. And with expander graph, it means the lambda here is less than 0.9. So this part is actually a simpler one. And I forgot to mention the second case here. Suppose we have the large agreement to each variable. We just say that supposing the violating constraint epsilon m is this, and this, and for each two nodes here in the two variables here, and there are at most epsilon m over 4 of them is not agreed with our choice. So in total, there are at most 2 epsilon m over 2. That is not at most them is changed. So that means at least epsilon m over 2 will reserve the same violated assignments. So there are at least epsilon m over 2 number of constraints inside which is violated. So we also can get the much better number of constraints here. So it's okay. And the last part, we want to make the constraint graph to be expander. So that is simpler because we can add some dummy edges. The dummy edges means suppose we add edges to variable I and variable j, and actually we just add an always true constraint or always true constraint between these two variables. So we can add any free edges. So actually, suppose the current constraint graph is H. We just keep this constraint here, and also we find an deregular in nd lambda. The expander graph here. It is suppose that is lambda is really small, say 0.1 here, and another diagonal with a large portion of self loops. There are d is equal to di, and so therefore this is a deregular graph. and this is a deregular graph expander, deregular expander graph, and this is just a bunch of self loops, a bunch of self loops. So we just add them all. That means is to add a lot of dummy constraints to phi so that the graph norm here is this is like so equal to 1, and this is 0.1, this is 1, and this is 1. So the sum of them will be by the exercise 11.7, we will get our new lambda of these things will be most 0.9, which is expander graph. And also, by means that we add a lot of self loop is to make sure every lambda here is will be far distance between it's all non-negative eigenvalues, so it will have we will not have some strange behavior such like the bipartite graph or something. So overall, we just go so far. We get a linear, the complete linear reduction, a linear blow-up reduction, so that phi is a nice instance that we want. So next to the next part, we will prove the rest of the things so that we can rescue the epsilon, the gap that we have just shrink, so to enlarge them again. Okay, so thank you.